Hello, I'm Martin Wimpress. I'm Senior Director for Developer Relations and Community at Slim.AI. Today I'll be sharing 5 practical examples of best practices to better secure your production-ready containers. I'll briefly introduce Slim.AI. Slim.AI was created to give developers the power to build safer cloud-native applications with less friction. In connection with our open source Docker Slim, the Slim.AI SaaS platform allows developers to optimize their containers, reducing both overall size and vulnerability count. By increasing efficiency and decreasing the attack surface, Slim.AI ensures you're only shipping into production what you need to. Today, I'm going to present 5 security best practices for your production-ready containers. I'll briefly introduce our sample application. Then I'll look at container best practices with a specific focus on where it impacts security. You should understand exactly what you're shipping into production. And I'll introduce several tools that can help with that you can start using today. We'll then make an objective decision on what the best base image is for our example application, and finally we'll minify the container image with Docker Slim to significantly reduce the attack surface. So we're going to use Python for our example. Here's a very simple Python Flask app that implements an even simpler RESTful API, and that app is just for illustrative purposes. Its function is unimportant. We could have done this example with Node.js, for example. We'll containerize this app using 4 different base images and several different container composition techniques. So let's just take a look at one of those Docker files. This Docker file adheres to container best practice. It uses an official Python base image. A work directory is defined for our app. It has good layer construction to minimize cache invalidation and optimize build performance. Files are copied only as required. A port is exposed, and it uses an entry point for proper signal handling. But there are a few things that can help specifically with container security. So let's take a closer look at each of those. If you do not specify a user in your Docker file, your app will run as root. Nobody is an unprivileged system account. It's available by default in Debian, Ubuntu, RHEL, Alpine, Distroless, etc. The Nobody account is intended to run things that don't need any special permissions. It's usually reserved for services so that if they get compromised, the would-be attacker has minimal impact or access to the rest of the system. By contrast, if the app is running in the root context, then the would-be attacker potentially has complete access to the container and possibly access to all the tools and utilities shipped in the container that they can now use to disrupt your operations. Choosing a version number for your base image is often referred to as pinning. Some tutorials teach newcomers to pin their images to the latest tag. However, containers are meant to be ephemeral, meaning that they can be created, destroyed, started, stopped, reproduced with ease and reliability. Using the latest tag means there isn't a single source of truth for your software bill of materials, resulting in your container getting whatever the most recently updated version is. A new version to the latest tag can introduce major version bumps to the system and the language, which will likely introduce breaking changes. Pinning a specific major and minor version in your Docker file is a trade-off. You're choosing to not automatically receive system upgrades and language improvements and fixes via the update mechanisms. But most DevSecOps teams prefer to employ security scanning as a way to control updates, rather than dealing with the unpredictability that comes with container build and runtime failures. We'll now see how pinning a base image tag can be helpful. Avoiding run apt-get upgrade in Docker files was considered best practice. It was considered best practice. In the vast majority of cases, this is not good advice. Base images from vendors and large projects are frequently updated using the same tag to include critical bug fixes and security updates. However, There can often be days between the updates being published in the package repositories and the revised base images being pushed to the registries. Relying on the base image alone is not sufficient, even from images blessed by Docker and maintained by companies with plenty of resources. Now imagine a small open source project maintained in somebody's spare time. If you pin a stable base image, package updates are purely focused on security fixes and severe bug fixes. You can safely apply system updates without fear of unexpected upgrades that may introduce breaking changes. But you do need to be sure you're really applying the latest updates. Docker builds can be slow, so we use layer caching to reuse build steps from prior builds to speed up the current one. And while this does improve performance, there's a potential downside. Caching can lead to insecure images. For most Docker file commands, if the text of the command hasn't changed, the previously cached layer will be reused in the current build. When you're relying on caching, those apt-get, install, update, upgrade, run commands will add old, possibly insecure packages into your images even after the distro vendor has released security updates. So sometimes you're going to want to bypass the caching. And you can do so by passing a couple of arguments to Docker build. --pull pulls the latest version of the base image instead of using the locally cached one. And --no cache ensures all additional layers in the Docker file get rebuilt from scratch instead of relying on the layer cache. If you add those arguments to Docker build, the new image will have the latest system level packages and security updates. But if you want the benefits of caching and get security updates in a reasonable amount of time, you'll need to have two build processes. Your normal build process that happens whenever new code is released, and a nightly process that rebuilds your container image from scratch using Docker build --pull --no cache to ensure you have all the security updates. So at this point we now have a container image that adheres to best practice, but what's actually inside it? I'm not going to deep dive into container vulnerability scanning and software bill of material generation. That could be a talk in its own right. However, you should absolutely perform vulnerability scans and generate SBOMs in your production container image build pipelines and review the results. These are also extremely useful tools for understanding what's in your containers, what you are shipping to production, and what your potential exposure is. For the purposes of this presentation, I have used Docker Scan, which is powered by Sneak, and Docker SBOM, which is powered by Sift. Other scanning utilities are available, such as Trivy, Gripe, and Claire. I do recommend that you give them all a try. I use the Slim.AI SaaS platform and more recently the Slim.AI Docker extension to demystify containers and really get to know what's inside them. Knowing what's inside your container is critical to securing your software supply chain. The Slim platform lifts the veil on container internals so you can analyze, optimize, and compare changes before deploying your cloud-native apps. Let's use container scanning and analysis to determine what the best base image would be for our example application. The regular official Python base image is built from Debian 11 and weighs in at 915 megabytes, but smaller starting points are available. I'll containerize our example app using 4 different base images, including the official Python image based on Alpine 315, the official Slim Python image based on Debian 11, a distroless multi-stage build, and Ubuntu 2204, which doesn't include Python by default, so has to be installed via a Docker run command. Sometimes it's necessary to install additional system packages as dependencies for your applications, or otherwise to help your build the image. The Ubuntu base image doesn't include Python, so it needs to be installed via apt-get using a Dockerfile run command. The default options for system package installation on Debian, Ubuntu and RHEL can result in much bigger images than expected. That 915 megabyte Python base image I mentioned earlier is a good example. More packages make the container image larger, which may in turn increase the attack surface of the container. So when you do need to install additional system packages, avoid installing the recommended dependencies. I've included examples here for Ubuntu and RHEL that install Python 3 without those unnecessary recommended packages. Using --no install recommends on my Ubuntu base container reduced the image size by approximately 266 megabytes. So let's build our app with each of those base images and see how those final image sizes stack up against one another. Here's the results in terms of image size. The images all include Python, our example app and its dependencies, and those dependencies are 11 packages that get installed via pip. The adage goes, smaller is safer. A smaller image size should correspond to fewer packages that should result in fewer vulnerabilities. So let's check that. There's no denying that these Alpine results are excellent with 0 vulnerabilities. The official Python image based on Debian 11 is not looking great, however, with 84 vulnerabilities, of which 13 are critical and 3 are high. And these are all in system packages installed via apt. Distroless, which is also based on Debian 11, has 46 vulnerabilities. Of those, 3 are critical and 7 are high. Again, these are all in system packages installed via apt. And with Distroless, it's also difficult to do much about this. Unlike traditional Debian-derived images, there is no apt-get in order to install the latest updates. It can be worked around, but it is non-trivial. And that brings us to Ubuntu, the largest container image, but the second best vulnerability assessment. No critical or high vulnerabilities at all, just 7 medium and 16 low-risk vulnerabilities. Well, why is this? Ubuntu is derived from Debian, right? Ubuntu is a commercially backed Linux distro with a full-time security team that has SLAs to mitigate vulnerabilities for their customers and users, which also includes mitigating all critical and high vulnerabilities for the supported lifetime of the distro. Debian, on the other hand, is a community project, and while many Debian contributors, including myself, do fix security issues in Debian, it simply cannot provide the same level of commitment to security as the commercially backed Linux vendors, such as Canonical, Red Hat and SUSE. So, looking at these results, Alpine is the clear winner, right? Well, sadly not. Python and Node and some other languages can result in significantly slower build times and introduce runtime bugs and unexpected behavior when using Alpine. This is due to the differences in muscle used in Alpine as opposed to glibc used in most other distributions. And this topic could also be a talk of itself. Personally, I do not recommend using Alpine for Python apps, but it can be great for Go and Rust. So, what if? What if I could have the low complexity of maintaining Ubuntu-based containers and the security profile of Alpine? And what if I can make containers smaller than Alpine? Well, let's try that. The terms slim, minify and optimized are used interchangeably to describe the act of reducing the size of a container image. Docker Slim is a free and open source software available from GitHub. Both Docker Slim and the Slim.AI SaaS platform can automatically optimize your containers. Don't change anything in your container image and minify it up to 30 times, making it more secure and reducing the attack surface of the container. Docker Slim has been used with Node.js, Python, Ruby, Java, Golang, Elixir, Rust, R, PHP, and all running on top of Ubuntu, Debian, CentOS, Alpine, Distroless, and more. We always get asked how Docker Slim works, so let's just take a quick look at that. Docker Slim optimizes containers by understanding your application and what it actually needs using various analysis techniques, including static and dynamic tracing. Docker Slim will throw away what the container doesn't need. A new single layer image is created, and it's composed from only those files in the original FAT image that are actually required by your app in order for it to function. You can understand your container images before and after optimization using the Slim.AI SaaS platform or the Slim.AI Docker desktop extension. There are also a number of benefits to slimming containers. Only ship to production what your app requires. Slim containers can be up to 30 times smaller than fat containers. Slim container images are faster to deploy due to their lower size and faster to start due to having fewer files inside them. Slim containers can be less expensive to store and transfer, and slim containers reduce your attack surface. In our report titled What We Discovered Analyzing the Top 100 Public Container Images, we saw an increasing trend in dev, test, QA and infrastructure tooling being left inside production containers. Unused shells, interpreters, tools, utilities left in your container images can be used against your infrastructure to disrupt your operations if a container is compromised. So let's take a look at those slimmed containers. In most cases, there are significant size reductions to be had slimming any container image, regardless of the build technique or base image used. In our example here, we're seeing between 3 and 5 times size reductions. Quite modest, but valuable all the same, as the container attack surface has been significantly reduced. We often see 10 to 30 times size reductions in complex applications. And our slim Ubuntu based image is now just 5 megabytes larger than the slim Alpine based image, but with none of the compatibility concerns and 37 megabytes smaller than the unoptimized Alpine image. But has slimming also improved the vulnerability assessment? Let's find out. Analyzing if vulnerable components exist in slimmed containers is currently a manual task, as the metadata the scanning tools use is often no longer available. That said, it only takes a few minutes at most, and using the Slim.AI SaaS or the Slim.AI Docker desktop extension to search for vulnerable components and confirm that they're no longer present. We've already confirmed the Ubuntu-based image was free of critical and high-risk vulnerabilities. The 7 medium-risk vulnerabilities were in E2FS progs, which are Linux file system utilities, libsqlite 3 and Perl base. It took literally seconds to confirm that none of those components exist in the slimmed image. So now we just have the low-risk vulnerabilities remaining. And 2 of those low-risk vulnerabilities were in the Python mailcap module, something we should be interested in given we have a Python application here, and it was specifically in the find match function. Again, it took seconds to use the Slim.AI Docker desktop extension to confirm that the Python mailcap module was no longer present in the slim image. In fact, let's do that now. So this is our unoptimized Ubuntu image with our app inside it. So let's just analyze that very quickly. We're going to search for mailcap because that's the Python module that we're interested in. So let's bring those results up. And we can see here is the mailcap module, and here the compiled bytecode for that module. So this is in the unoptimized image, so we can confirm that there it is. It's present. But now what we'll do is we'll look at the slim image. So we'll analyze this one and we'll do the same search. So we'll search for mailcap, and as you can see, no results have come back. So this is great. We had a Python app with a vulnerable component. Our app doesn't use that component, so consequently, that vulnerability is entirely absent from our resulting container. A couple of minutes was all that was required to use the Slim.AI Docker desktop extension to confirm that all of the components affected by the remaining 6 low-risk vulnerabilities have also been entirely removed. So yes, we can have our cake and eat it too. We have an Ubuntu-based image with no known vulnerabilities of comparable size to a slimmed Alpine image, but with none of the potential complexity of working with Alpine. It's also worth noting that the high-risk vulnerability CVE 2021-3999 in glibc that exists in the distroless and official Python images that are based on Debian 11 was still present in those images, unlike Ubuntu, where it's already been mitigated, and unlike Alpine, where it never existed by virtue of Alpine using Muscle. So therefore, in this case, Ubuntu is the best base image for our example application. So let's take a look at what we've learned. Following container best practice will set you up for success. Always run internet-facing apps and services via unprivileged user accounts. Pin your base images. Use a stable base image and apply your security updates. Be mindful of layer caching, introducing potentially insecure packages into your container images. Container scanning and analysis are essential to fully understand what's inside your containers. Do not install recommended packages to help keep your containers slim and secure. Linux vendors have security SLAs. Assess your base image options and pick what is most suitable for your project. You can slim just about any kind of container image, including those based on Alpine and distroless, and slimming significantly reduces vulnerabilities and the attack surface. But yes, that was more than 5, and you're welcome. So thanks for listening. I hope you've picked up a few tips to help improve the security of your containers. We invite you to give Slim.AI SaaS and the Slim.AI Docker extension a try. Both are free to use, and also take Docker Slim for a spin. If you have follow-up questions, then join the Slim.AI Discord and ask, or you can follow us on Twitter and ask there. Keep building and enjoy the rest of the conference.